Okay, good morning, everyone. So this is the title of my talk, and I'm also giving a poster on the same topic. So feel free to come to the poster as well. Let me introduce the system which we are using, which is exciton-polariton condensate, which is the superposition of exciton and photon, and is formed in a microcavity. This is the schematic of how it is formed in the microcavity, and these are the dispersion curves of upper polariton, lower polariton, and the original photon and exciton branches. Now, these polaritons are bosonic in nature, and it tends to form a condensate just like other atomic bosons. But these polaritons, since are superposition of exciton and photon, it inherits properties from both exciton as well as photonic components. And it gets the lifetime from the photonic components, and it happens to be very short-lived of the order of some picoseconds. So as such, these are dissipative systems and cannot form a stable condensate. In order to have a stable condensate, the requirement is external pumping, which can be obtained and is known in literature by two ways. One is a coherent pumping, another is an incoherent pumping. In case of coherent pumping, the cavity is pumped with a monochromatic light resonant to the lowest energy of the lower polariton. And the incoherent pumping, the cavity is pumped with a light at a slightly higher energy, where the lower polariton behaves more like an exciton. And we get an excitonic reservoir. So instead of a direct pumping to the lowest energy state, it's an indirect pumping, and the equation of motion for the condensate is given by this coupled equation, where this equation is a driven-dissipative Gross-Pitavsky equation, which is the underlying structure is just like a Gross-Pitavsky equation, apart from the drive and the dissipation terms. And this is the equation of state for the reservoir. Now, for our study, we are considering a specially uniform pump, which is P0, and below a threshold. The threshold pump is defined when there is balance of gain and loss phenomena. Below the threshold pumping, there is no condensate formed. Above the threshold pumping, the condensate is formed, and it is stable if this condition is satisfied. This can be further reduced between a competition between the damping rates of excitons and polaritons, saying that the rate at which the excitons damp from the reservoir is much faster than the rate at which the polaritons leaves the microcavity. This is the condition required for a stable condensate. Which one? Yeah, this is the strength of the pumping we are choosing. P is the general form of pumping. For our case, we have taken a specially uniform P0 for pumping. Okay. So we are interested to study the dynamical regions of the exciton-polariton condensate, and we can identify few specific dynamical regions if we see the different time scales associated in the equations. These are the different time scales, where each time scale is associated with the individual terms in the equations of psi and n, where this tau kinetic is basically associated with the kinetic energy term, gain loss is associated with the gain loss term, SI and CI are the self-interaction and cross-interaction time scales, and tau r is the reservoir time scale. So if the reservoir time scale happens to be smallest time scale in the dynamics, then we can get these inequalities, and it is possible to adiabatically remove the reservoir from the equation of motion. So instead of these coupled equations, we can reduce to a decoupled equation of the condensate. And this regime is identified as the adiabatic regime. If any of these inequalities are not valid, then it is called the non-adiabatic regime. For our case, we have chosen the non-adiabatic regime, stating that all these inequalities are not valid. So these are the two regimes we are using, and we will be studying this further. the non-adiabatic regime where the equation of motion happens to be a coupled Gross-Pitavsky equation, driven-dissipative Gross-Pitavsky equation, and the adiabatic regime where the equation of motion is a uncoupled Gross-Pitavsky, driven-dissipative Gross-Pitavsky equation, and these are the inequalities for these regimes. Now, the motivation of this work is to understand the hydrodynamics of the condensate in both these regimes. If you look at the original equations of Chi and N, and also Chi in this regime, the features like nonlinearity, dispersion, damping, which happens to be the characteristics of hydrodynamic equations, are not that transparent because of the complicated nature of these equations. So we can use a formalism where these original equations can be mapped to equivalent chiral equations where these features are more transparent. I will introduce that in this slide now. So the formalism for getting chiral PDE starts from writing the hydrodynamic equations for which we use this Madelung transform. Rho is the density and V is the velocity field. So we get the hydrodynamic equations in terms of rho and V. Next, we linearize the fields about a fixed background. Let's say Q is the rho or V kind of field, Q0 is the fixed background, and delta Q are the linear fluctuations. So then at this stage, we get the hydrodynamic equations of the fluctuations. Next, we introduced a scaling procedure where we scale the spatial and temporal variables in terms of this small parameter epsilon, which happens to be a small perturbation. And the hydrodynamic equations reduces in this form, where this L is a linear operator and N is a nonlinear operator. Next step, we introduce a perturbative scheme where this, the solution is expanded in terms of epsilon square in this way, and we substitute this here and we collect the coefficients of each order. At the lowest order, we get the linear equation, and the solution can be obtained if we get the null space of this linear operator. This is the solution of the linear problem where V and lambda are the eigenvectors and eigenvalues of the linear operator. For the next order, the equation seems like this, where in the left-hand side, we have a non-invertible matrix. So for getting the solution, we have to invert a non-invertible matrix. For this, we use Fredholm alternative, which states that a solution exists if and only if this right-hand side is orthogonal to the null space of the adjoint of the linear operator, which is L dagger. Now this condition which is imposed to the right-hand side, it gives an equation of this unknown function alpha of the previous order, and which happens to be chiral PDEs for the original hydrodynamic equations. So this formalism has been earlier studied by Svetlana, Vishal, and Manas in a recent paper for hydrodynamic for Hamiltonian systems. We will be using the same formalism because this does not restrict only to the Hamiltonian systems. For our system, this is a non-Hamiltonian system, and we will be using the same formalism for both adiabatic and non-adiabatic regimes.
Chiral because it depends on x minus lambda.
Yes, it has some direction associated with it. Yeah. So we use the same formalism for the non-adiabatic and adiabatic regime. So for the non-adiabatic regime, we get these three PDEs, where the first one is moving to the right, the second one is moving to the left, and the third one is diffusive in nature, and it is not moving. Similarly, the adiabatic regime, this dynamics decouples to these PDEs, where the first one is right moving and the second one is left moving. And these happens to be the chiral PDEs, the right and left moving are the chiral PDEs for non-adiabatic and adiabatic regime. Now, if you look at the structure of these PDEs, these are more like generalized form of KdV, more like damped KdV. So we can identify this as the nonlinear term, this as the dispersion term, and this as the damping term. Now, since I have already argued that this formalism or these chiral PDEs makes the features more transparent, this can be clear from these equations. Let me again consider the same equation, which is the chiral PDE for the adiabatic case, as I've mentioned that each term here has a specific feature associated with it. For instance, this is a nonlinearity term, this is the dispersion term, and this is the damping term. And each of these terms can be associated with certain time scales. Let's say we choose an initial profile with the height u and width w, then we can identify certain time scales associated with the strength of nonlinearity, dispersion, and damping. Saying that if omega 1, which is the inverse time scale for the strength of nonlinearity, happens to be the maximum among 3, then during the time evolution, the first feature which kicks in is nonlinearity, then dispersion and damping. Similarly, we can identify the different length scales, which are these length scales. For instance, if the width is equal to W12, it implies that nonlinearity and dispersion plays the same role in the time evolution of the profile. So these kind of estimates are not possible from the original equations, but these chiral PDEs makes it more sustainable to identify these time scales in terms of the features involved in the hydrodynamics of the problem. Here we have compared the original equations and the effective theory which reduces to these chiral PDEs, for which we have, since these are generalized versions of KDV, we have used the initial condition as the KDV solitons. We have mapped it to the in terms of the original parameters and get the initial conditions for the original equations. These are the time evolution of density for different time steps. We can see that for both non-adiabatic and adiabatic regime, the two methods, the original dynamics and the effective dynamics, matches very well qualitatively. So this recipe also suggests a way to give sustainable initial conditions for the original dynamics. So now I would like to conclude that this effective theory gives PDEs for the non-adiabatic and adiabatic regimes, which happens to be generalized version of KDV and diffusion equations. This is a powerful method to find optimal initial conditions for the original equation that evolve as robust as possible. The effective theory agrees very well with the original dynamics qualitatively, and it makes the dynamics hidden in the cryptic equations more transparent. I would also like to say there is another poster by Raghavendra. He will be using the same formalism for dynamics of multi-component, multi-soliton, nonlinear Schrodinger equations. Please do visit his poster for more details. Thank you.
We have time for a couple of questions, so if there is any, just shoot them out.
Yeah.
In the adiabatic regime and the other,
the non-adiabatic regime.
Non-adiabatic regime,
yeah.
You had two equations in
Yes.
in the non-adiabatic regime and three
Two
equations
in the adiabatic and 3 in the non-adiabatic. Yes,
yeah.
yes.
So why is that so? What extra?
Yeah, it's because the rank of the matrix. Okay, if I go back here, okay, this is a coupled PDE, right? The starting equation is a coupled equation. Here it is a single equation. So here the variables or the linear equation, which is the first order problem which we are solving, is the linear operator. It happens to be a 2 by 2 matrix. So the eigenvalues are only 2. Here there are the linear operator itself is a 3 cross 3 matrix, and we have 3 eigenvalues. So each eigenvalue reduces to a PDE by this formalism. So that's why you're getting 3 for the non-adiabatic regime and 2 for the adiabatic regime.
You impose that linear condition, right? L dagger acting on the right-hand side was
Yes.
0. But how did the nonlinear terms come from that linear condition?
Oh, yeah. Okay. So the way we are introducing nonlinearity in this equation, it will kick in the next order, but it is a function of delta Q naught, right?
Oh, I see.
So you know delta Q naught. So when you're solving the right-hand side, you don't need explicitly delta Q1, and you can solve that to get the PDE.
So the nonlinearity is coming from that n of delta
Yes,
Q naught.
yes, exactly.
If there are no more questions, then we would thank the speaker once again. Yeah.